why mathematics is not real. Let me tell you something that no physicist is supposed to say out loud, something that will make my colleagues uncomfortable, something that undermines the very foundation of everything I've spent my career doing. Mathematics is not real. It's the equations we write on blackboards, the formulas we use to predict the behavior of particles and planets and black holes. They're not describing reality, they're describing something else entirely. And the difference between what math describes and what actually exists out there in the universe is so profound, so disturbing, that most physicists refuse to even think about it. I'm Leonard Susskind, and after 50 years of working with mathematics every single day, of living inside equations, of dreaming in symbols and integrals and differential geometry, I've come to a conclusion that shakes me to my core. We have been confusing the map for the territory, and the territory, the actual physical universe, might be nothing like the map at all. Let me start with something that sounds obvious but isn't. When you look at the night sky, you see stars, points of light scattered across the darkness. Beautiful, simple, real. Now, when a physicist looks at those same stars, they see something very different. They see nuclear fusion equations. They see hydrostatic equilibrium. They see the Hertzsprung-Russell diagram. They see Stefan Boltzmann law and mass luminosity relations and spectral classifications. They see mathematics. And here's the question nobody asks. Are those equations up there in the sky? Is the Stefan Boltzmann law floating around inside the star telling it how to shine? Or is the math something we invented, something purely human that we project onto the universe because our brains need patterns to survive? This is not a trivial question. This is arguably the most important question in all of science. And physicists have been dodging it for centuries. Let me give you the standard story first. It's the one you'll hear in every physics lecture, every popular science book, every documentary. It goes like this. Mathematics is the language of nature. The universe is written in mathematical code. Galileo said it first. The book of nature is written in the language of mathematics. And ever since then, physicists have treated this as gospel. We discover a new phenomenon. We write an equation for it. The equation makes predictions. The predictions come true, therefore mathematics is real. It's out there. It's woven into the fabric of the cosmos. This is called mathematical Platonism. The idea that mathematical objects, numbers, triangles, equations, infinite dimensional Hilbert spaces, that these things exist independently of human minds. That they would exist even if no humans had ever evolved, that a circle is a circle whether or not anyone is around to draw one. And I used to believe this, I really did. When I was young and first discovering the power of mathematics to describe physics, it felt like revelation. Like I was uncovering something that had always been there. It's like the equations were truths waiting to be found, not inventions waiting to be built. But the more I've thought about it, the more problems I see. It's deep, fundamental, unsolvable problems with the idea that mathematics is real. Here's the first problem. The unreasonable effectiveness of mathematics. In 1960, the physicist Eugene Wigner wrote a famous paper with exactly that title. He pointed out something remarkable. Mathematics works far better than it has any right to. We develop mathematical tools for purely abstract reasons with no connection to physics whatsoever, and then decades or centuries later, those tools turn out to be exactly what we need to describe. Some newly discovered physical phenomenon. Riemann developed his geometry of curved spaces in the 1850s as a purely mathematical exercise. 60 years later, Einstein used Riemannian geometry as the foundation of general relativity. The mathematics of curved spacetime was sitting there, ready and waiting, decades before anyone knew spacetime was curved. Group theory was developed by mathematicians in the 1800s, studying the symmetries of algebraic equations. A century later, it became the essential language of particle physics. Every fundamental particle we know, every force, every interaction is classified by its group theoretic properties. The mathematics preceded the physics by 100 years. Now, if you're a mathematical Platonist, this makes perfect sense. The math was always out there, the mathematicians discovered it, the physicists discovered that nature uses it. Beautiful story. But think about it more carefully. If mathematics is real, if it exists out there in some abstract realm, then why does only some of it correspond to physics? Because here's the thing. For every piece of mathematics that successfully describes reality, There are thousands of mathematical structures that describe nothing at all. Mathematicians have invented, or discovered, if you prefer, an enormous landscape of mathematical objects, infinite dimensional spaces with exotic topologies, non-commutative geometries, surreal numbers, transfinite cardinals, category theory in all its abstract glory. Most of this mathematics corresponds to nothing in the physical world, not as far as we know. So if math is real, if it exists independently of us, then we live in a universe that uses only a tiny, tiny fraction of all possible mathematics. The rest of it exists, but does nothing. It's like having a library with 1 billion books and discovering that the universe only reads 3 of them. That's strange. That requires explanation. And here's the deeper problem, one that has haunted me for decades. When we say mathematics describes reality, what do we actually mean? Let me give you a concrete example. Let's take Newton's law of gravitation, F equals g times m1 times m2 over r squared. This equation tells you the gravitational force between two masses. It's incredibly accurate for most everyday situations. It predicted the existence of Neptune before anyone saw it. It got us to the moon. But here's what the equation doesn't tell you. It doesn't tell you what gravity is. It doesn't tell you why masses attract each other. It doesn't tell you what force actually is at a fundamental level. It gives you a number. It's a very accurate number, but a number is not an explanation. A number is not reality. It's a description. There's a world of difference. Then Einstein came along and said Newton was wrong. Gravity isn't a force at all. It's the curvature of space-time. Mass tells space-time how to curve. Space-time tells mass how to move. Beautiful, profound, a deeper description. But notice what happens. The mathematical description changed completely. Newton's equation was replaced by Einstein's field equations. Completely different mathematics. The physical phenomenon, things falling, planets orbiting, didn't change at all. The universe didn't change. Only our mathematical description changed. And Einstein's equations are more accurate than Newton's, but they're still not perfect. They break down at singularities. They're incompatible with quantum mechanics. Someday we expect them to be replaced by something even deeper, a quantum theory of gravity with yet another mathematical framework. So here's my question. If the math keeps changing, if we keep replacing one set of equations with another, each more accurate than the last, but each fundamentally different in structure, then in what sense is any particular set of mathematics real? Newton's math was real for 200 years. Then it wasn't. Einstein's math has been real for 100 years. Someday it won't be. If mathematical reality keeps shifting under our feet, maybe it was never reality in the first place. Maybe it was always just approximation, useful, powerful, astonishingly accurate approximation. But approximation nonetheless. Let me push this further. Consider quantum mechanics, the most successful theory in the history of science. Its predictions have been confirmed to 12 decimal places. It's 12, that's like predicting the distance from New York to Los Angeles to within the width of a human hair. And quantum mechanics is pure mathematics. The wave function Hilbert spaces. It's Hermitian operators, complex probability amplitudes. None of these have any obvious counterpart in everyday reality. You cannot point to a wave function. You cannot touch a Hilbert space. You cannot photograph a probability amplitude. These are mathematical abstractions. And yet they work, they predict the outcomes of experiments with incredible precision. They underpin all of modern technology, every computer chip, every laser, every MRI machine. But here's the disturbing thing. We don't know what quantum mechanics means. We know what it predicts. So we know how to use it, but we have no idea what it's telling us about reality. The wave function, is it real? Does it exist out there in the universe? Or is it just a mathematical tool for calculating probabilities? This is the measurement problem, the interpretation problem. And after nearly 100 years of arguing about it, physicists still don't agree. Some say the wave function is real, that it's the most real thing there is. That's the many worlds interpretation, where every quantum possibility is actualized in some branch of reality. Others say the wave function is just information. It encodes what we know about a system, not what the system is. That's more in line with Copenhagen or Cubism. Others say the wave function is a mathematical fiction that produces correct predictions but doesn't correspond to anything physical. These aren't minor disagreements about details. These are fundamental disagreements about the nature of reality. And here's the kicker. All of these interpretations make exactly the same predictions. You cannot design an experiment to distinguish between them. The mathematics is the same regardless of which interpretation you choose. Think about what that means. The math works perfectly, but it doesn't tell us what's real. Multiple completely different pictures of reality are compatible with the same mathematics. The math underdetermines reality. It constrains what's possible, but doesn't determine what actually is. If mathematics were reality, if the equations were the truth, then there shouldn't be multiple interpretations. There should be one picture, one reality. The equations should tell us what exists. But they don't. They tell us what we'll measure, and what we'll measure is not the same as what exists. Now, let me tell you about something that deepens this mystery considerably. The role of symmetry in physics, modern physics, is built on symmetry principles. The standard model of particle physics, the theory that describes every known particle and every known force except gravity, is built entirely on gauge symmetries. These are mathematical symmetries, abstract transformations that leave the equations unchanged. And the particles, the physical things, the things that actually exist and can be detected in labs, they are representations of these symmetry groups. But here's the strange thing. Are the symmetries real, or are they features of our description? Consider gauge symmetry. In electromagnetism, there is an infinite family of mathematical descriptions that all give the same physical predictions. So you can change the gauge, the mathematical description, in arbitrary ways, and all the physics remains the same. It's only certain combinations, certain gauge invariant quantities correspond to anything physical. The rest is mathematical redundancy. We put it in to make the equations work. It's not out there in the world. It's in our description of the world. This is deeply puzzling. The most fundamental theory we have, the standard model, is built on gauge symmetries that are, in a precise sense, not real. They're artifacts of our mathematical formalism. The real physics, the measurable physics, is gauge invariant. It doesn't care about the mathematical redundancy we've introduced. So we build our deepest theories on mathematical structures that we know are partly fictional. We know that gauge freedom is not physical. We put it there for mathematical convenience. And yet the theory works spectacularly well. What does this tell us about the relationship between mathematics and reality? I think it tells us that mathematics is a tool, spectacularly powerful tool, but a tool nonetheless like a hammer. A hammer is incredibly useful for driving nails, but the hammer is not the nail. The hammer is not the wall. The hammer is not the house you're building. It's the thing you use to build the house. Mathematics is the thing we use to build our understanding of the universe, but it's not the universe itself. Let me give you an analogy that I think captures what's going on. Think about a map, a good map of, say, London. It shows you the streets, the parks, the river, the buildings. It's incredibly useful. You can navigate the entire city with a good map. The map makes predictions. If you walk north on this street for 3 blocks and turn left, you'll reach the park, and those predictions come true. But the map is not London. The map is made of paper and ink. London is made of concrete and brick and people and history. The map represents London. It corresponds to London in systematic, reliable ways, but there are things about London that no map captures: the smell of the Thames, the sound of traffic, the feeling of rain on your face. The map is two-dimensional. London is three-dimensional. The map is static. London is dynamic. No matter how detailed you make the map, it will never be London. Mathematics is our map of the universe. And like any map, it captures some features of the territory and misses others. The features it captures with breathtaking precision, but the features it misses might be the most important ones. What does it miss? Maybe consciousness, maybe the intrinsic nature of matter, maybe the reason anything exists at all. Maybe the thing that makes the present moment feel special, even though the block universe says it isn't. Mathematics gives us structure and relations. It tells us how things relate to each other. Mass relates to energy by E equals mc squared, but it doesn't tell us what energy is, not fundamentally, not in itself. It tells us how energy transforms, how it's conserved, how it flows from one form to another. But the thing itself, The stuff that the math describes remains mysterious. This leads me to something that I find genuinely disturbing. And I don't say this lightly. What if the universe is not mathematical at all? What if mathematics works not because reality is made of math, but because our brains are? Think about it. Our brains evolved to survive, to find food, avoid predators, navigate terrain, predict the behavior of other humans, and the way our brains do this is through pattern recognition. We're pattern matching machines. So we see patterns everywhere, even where they don't exist. Constellations and random stars, faces in clouds, meaning in noise. Mathematics is the most sophisticated form of pattern recognition ever developed. It takes the raw chaos of the universe and imposes order on it. Numbers, categories, relationships, structures. And it works because the universe, at the scales we evolved to perceive, does have regularities. Objects fall predictably. Seasons cycle, predators follow prey along predictable paths. But the regularities might be approximate, they might be local, they might be features of our scale, our energy regime, our corner of the cosmos, not features of fundamental reality. And the mathematical structures we build to capture those regularities might be exactly that, structures we build, not structures we discover. Here's evidence for this view that I find compelling. It's mathematical paradoxes. If mathematics were a feature of reality, if it existed independently of human minds, then it should be consistent. Reality doesn't contradict itself, but mathematics does. Gödel's incompleteness theorems proved in 1931 that any sufficiently powerful mathematical system is either inconsistent or incomplete. It either contains contradictions or there are truths it cannot prove. This is not a minor technical result. This is a fundamental limitation of mathematical systems. It means mathematics cannot be a complete, self-contained description of anything, including itself. Russell's paradox showed that naive set theory, the foundation of all mathematics at the time, was self-contradictory. The set of all sets that don't contain themselves, does it contain itself? If it does, it doesn't. If it doesn't, it does contradiction. Mathematicians patch this with more sophisticated axiom systems, but the patches are exactly that. Patches, human choices about how to formalize mathematics. Different axiom systems give you different mathematics. The axiom of choice, for example, you can accept it or reject it. Both options give you a consistent mathematical system, but with very different properties. If mathematics were real, there should be a fact of the matter about whether the axiom of choice is true. But there isn't. It's a choice, a human choice. That doesn't sound like discovering pre-existing reality. That sounds like building a tool and deciding which features to include. And then there's infinity. Mathematics is full of infinities, infinite sets, infinite series, infinite dimensional spaces, and these infinities are essential to the math we use in physics. It's quantum field theory. The theory underlying the standard model is riddled with infinities. Its calculations routinely produce infinite answers that we then have to renormalize, essentially subtract one infinity from another to get a finite result. It's Richard Feynman, who helped develop renormalization, called it a dippy process. He was being polite. It works. The predictions after renormalization are the most accurate in all of science. But the fact that the raw mathematics produces nonsense, infinity, and we have to manually intervene to extract sense from it, this should trouble us. If mathematics were the language of nature, if the equations were describing reality directly, why would nature speak in infinities that have to be manually removed? So I think the answer is that nature doesn't speak in infinities. Nature does whatever nature does. The infinities are artifacts of our mathematical description. They appear because our mathematical tools are imperfect representations of whatever the underlying reality actually is. The tool breaks down at certain limits and we patch it up. But a perfect description of reality shouldn't need patching. This is why so many physicists believe that quantum field theory, for all its success, is not the final word. There must be a deeper theory, maybe string theory, maybe something we haven't imagined yet, where the infinities don't appear, where the math is cleaner. But notice, even this hope assumes that there exists a perfect mathematical description. That's the Platonist assumption. And I'm not sure it's warranted. Let me tell you about something from my own work that made me rethink all of this. The black hole information paradox in the 1970s, Stephen Hawking showed that black holes radiate. They emit thermal radiation and slowly evaporate, and he argued that this process destroys information. The quantum state of whatever fell into the black hole is lost forever when the black hole evaporates. This contradicted a fundamental principle of quantum mechanics that information is always conserved. I spent years working on this problem. Ultimately, I and others argued that Hawking was wrong. Information is not destroyed. It's encoded in subtle correlations in the Hawking radiation. The information gets out. Quantum mechanics is preserved. But here's what struck me during those years of work. The entire debate was conducted in mathematics, equations, calculations, thought experiments translated into formalism. And at every stage, the mathematics was ambiguous. Different mathematical approaches gave different answers. Hawking's calculations said one thing. String theory calculations said another. Each was mathematically rigorous. Each was internally consistent. But they couldn't both be right about the physical world. The mathematics didn't resolve the paradox. The mathematics created the paradox. The paradox exists because we have multiple mathematical frameworks, general relativity and quantum mechanics, that are individually successful but mutually incompatible. If mathematics were reality, this shouldn't happen. Reality doesn't contradict itself, but our mathematical descriptions of reality absolutely do. Now, I want to be very clear about something. I'm not saying mathematics is useless. I'm not saying we should abandon equations and go back to qualitative hand-waving. Mathematics is the most powerful tool humanity has ever developed for understanding the natural world. Nothing else comes close. But a tool is not the thing it operates on. A microscope reveals the cellular structure of living tissue, but the microscope is not the cells. The cells exist independently of the microscope. And if you built a different kind of microscope, an electron microscope instead of an optical one, you'd see different features of the same cells, different resolution, different aspects revealed. It's both real, both partial. Our mathematical theories are like different microscopes. Each one reveals certain aspects of physical reality with extraordinary precision. But each one also has blind spots, limitations, scales where it breaks down, and the aspects they reveal might not be all there is. There might be features of reality that no mathematical microscope can capture. Not because we haven't found the right math yet, but because mathematics, by its nature, can only capture certain kinds of features. Structural features, relational features, quantitative features. What about qualitative features? The redness of red, the painfulness of pain, the nowness of now. These seem to be genuine features of reality, but no equation captures them. No mathematical structure explains what it's like to see the color blue. You can describe the wavelength. You can model the neural processing. You can write equations for the electromagnetic radiation entering the eye, but none of that tells you what blue looks like. This is the hard problem of consciousness, and it haunts the relationship between mathematics and reality. If mathematics were truly the language of nature, if reality were fundamentally mathematical, then consciousness should be derivable from the equations. But it isn't. After centuries of physics and decades of neuroscience, we have no mathematical description of subjective experience, not because we haven't tried hard enough. It's because the kind of thing consciousness is might not be the kind of thing mathematics can describe. And this connects to something even more radical. The idea that mathematics doesn't describe what reality is made of. It describes how reality behaves. There's a crucial difference. Behavior is external. It's what you observe from outside. It's what a system does, how it responds. Structure is what you can map and measure. But the intrinsic nature of things, what they are in themselves, this might be beyond the reach of any mathematical description. It's Bertrand Russell, one of the greatest mathematical logicians who ever lived, realized this in the 1920s. He pointed out that physics tells us about the causal structure of the physical world, about how events relate to each other, but it tells us nothing about the intrinsic nature of the entities involved. We know how electrons behave. We know their charge, their mass, their spin. But we don't know what an electron is. Not in itself. We know its mathematical properties. But mathematical properties are relational. They tell you how the electron relates to other things. They don't tell you what it is when it's just being an electron, not interacting with anything. This gap between mathematical description and intrinsic nature might be unfillable. Not because science is limited, but because mathematics by design captures relations and structures. It's what math does, and that's incredibly powerful. But if reality has an intrinsic aspect that goes beyond relations and structures, then mathematics will always be incomplete as a description of reality. Not wrong, not useless, incomplete forever. Some physicists will disagree with me. They'll say, Lenny, you're wrong. Mathematics is reality. The universe is a mathematical structure. Max Tegmark at MIT has proposed exactly this. His mathematical universe hypothesis says that the physical universe doesn't just have mathematical properties. It is a mathematical structure, nothing more, nothing less. Every mathematical structure that exists, and in Platonism they all exist, is a physical universe. We just happen to inhabit one particular structure. It's a bold idea. I'll give Max credit for that. And it's logically possible, but I find it deeply unsatisfying. Because if the universe is a mathematical structure, what makes it physical? What gives it substance? What makes it more than just an abstract pattern in some Platonic realm? Mathematical structures, if they exist at all in the Platonic sense, are causally inert. They don't do anything. They don't change, they don't evolve, they just are timelessly and eternally. But the physical universe does things. It evolves, it has a history, it produces stars and planets and people. Something about our universe is more than structure. Something breathes fire into the equations, as Hawking once put it. And that fire, whatever it is not captured by the equations themselves. Here's where I end up. After 50 years, mathematics is humanity's greatest invention, not discovery invention. We created it, we built it. We refined it over millennia, developing ever more sophisticated tools for describing the patterns we observe in nature. And those tools work astoundingly well. They predict, they explain, they unify. They reveal connections we never could have seen otherwise. But they are not reality. They are maps, brilliant, beautiful, extraordinarily detailed maps. Maps that have guided us to the moon and into the atom and to the edge of the observable universe, but maps that will always inevitably be less than the territory they represent. The universe is not made of mathematics. The universe is made of whatever the universe is made of. It's something physical, something concrete, something that has an existence and a nature that goes beyond any equation we will ever write. We use math to describe it. We use math to predict it. We use math to understand it, partially, incompletely, but powerfully. And maybe that's enough. Maybe knowing that our tools are tools, that our maps are maps, that the equations are not the cosmos, but merely our best representation of it. Maybe that's a kind of wisdom. It's the wisdom of knowing the limits of our knowledge. The wisdom of holding our deepest theories lightly, knowing their approximations, brilliant approximations. But approximations of something far stranger, far richer, far more real than any equation could ever capture. You know, when I look at the night sky now, I don't see equations anymore. I used to see the inverse square law in every point of starlight. I used to see Boltzmann distributions in the colors of stars and Hubble's constant in the redshift of galaxies. And those things are all there, in a sense. They're in my description of what I'm seeing. But what I'm actually seeing, the light itself, the photons hitting my retina, the ancient nuclear fire of distant suns, that's something else entirely. Something that no equation has ever fully grasped, something that exists whether or not anyone writes a single symbol on a single blackboard. The universe was here before mathematics. It will be here after the last mathematician is gone, and it will continue doing whatever it does with supreme indifference to whether we have the right equations to describe it. That's both humbling and liberating. Humbling because it means our greatest intellectual achievement, mathematics, is still just a shadow on the wall of Plato's cave. And liberating because it means reality is deeper, richer, and more mysterious than anything we've yet imagined. Thank you for listening. Let's go look at the stars tonight. And remember, what you're seeing is not an equation. It's something far more extraordinary than that. It's real, whatever that means.